Okay, we're back. Now, we've talked about what a mineral is. We've talked about the chemistry that goes along with the minerals. Now we're going to talk about a little bit about the properties. Now, the properties of a mineral actually are dependent upon the chemistry and how it bonds together, or what elements you have to give it the different defining properties that you have. Because each element has different properties as well. So when you combine those properties in bonding, you also will have different properties. For example, if you have sodium, remember it's a very reactive metal. If I put some sodium, pure sodium in water, it actually explode. Chlorine is a gas, and if you were to breathe it, it would actually be poisonous to you, so you die. Now, if you actually put the two together, then those properties, that very reactive gas, solid, and that very reactive gas coming together, now they become inert, and we have table salt, right? So the properties can change based off of the combination or the chemical bonding of those different properties, those different elements within it, okay? So when we classify a mineral, we classify it based off of their actual physical properties. And there's lots of different ones that we look at. We look at what we call its crystal form. This is an example of crystal form right here. This is called aragonite. And you can see the actual kind of octagonal kind of structure or crystal form of this mineral. Now this quartz that I have also has a crystal form to it as well. You can see the distinct crystal shape to it. It has kind of an octagonal shape as well, right? Well, there's other minerals that also have different shapes. Some of them are cubes. Some of them are what we call dodecahedral with 10 different sides and different things like that. Okay, so there's lots of different types. Now, cleavage, though, is what we call fracture. You probably understand this when you think about glass or something like that, or ceramics, where it breaks. It will break off of a random location to form this fractured plane. Whereas cleavage, okay, is when a mineral will break along a specific plane. Now this mineral is what we call biotite, and notice it's how flat it is here, and so it will break along this surface. If I don't want to do it with this mineral because this is a sample that I have, but if you look at it, you actually can pull apart in these different planes, okay, and because one side, the bonds in this direction and this direction are strong bonds, okay? Very strong bonds, covalent bonds. But the bonds in this direction are not very strong, and therefore they will want to cleave in the direction of that weak bond. So if I pull it apart, there will be that weak bond between this plane and the plane beneath it, right? And so that would be what we call cleavage. And certain minerals will cleave along certain directions or break in certain ways to actually form that. So for example, in table salt, if you look at table salt, you look at your sea salt at home or whatever, they're always in cubes. If you break it, it will break into cubes more because it will actually naturally want to break along specific planes or bonds to be able to make that form. Luster is just how the light is shining back on a mineral. For example, this one here has kind of a shiny luster to it. You can see the shine of it. It's black, but it still has that shiny luster. Okay. You have the quartz here, which you often call a glassy or virtuous luster, right? Okay. If I had some other ones here, I don't have a lot of rocks in front of me right now, but some could be like an earthy luster, where it looks kind of like dirt or soil, or a dull luster, or a metallic luster. It's any way that the light reflects back off of material. Color is one that's not very diagnostic for minerals, because a lot of minerals have different colors. For example, this quartz here this one's a clear one, but if you have purple quartz, it's amethyst. If you have a pink quartz, we call that rose quartz. If you have a kind of a black quartz, we call that smoky quartz. There's lots of different types of it. For example, another example is like an emerald. An emerald is a green beryl, or a blue a blue beryl is what we call a sapphire. And so the color can be different in a specific mineral. An emerald and a sapphire is the same exact mineral. The only difference is the impurities inside that mineral, which make it a different color. Okay. Now some minerals, though, are very distinctive colors, and so that can be used as a classifier. The streak, basically what the streak is if you crush up a mineral into small pieces, or as we grind it on a plate, it will leave behind a powdered form, and we call that the streak, the color of that powdered form. So like graphite for your pencil lead has a gray streak, because as you're writing with your pencil, you're actually leaving behind pieces of that graphite on your piece of paper, right? And so it has a grayish kind of streak. Hardness is just how hard the mineral is, and this is actually usually characteristic of the bonds that are associated with it. If you have strong bonds, it's usually harder. If you have soft bonds or weak bonds, it'd be a softer mineral, and we can break it easier, right? Or it's resistant. What basically hardness is its resistance to scratching or the breaking of those bonds, really. Specific gravity is how heavy it is or how dense it is. Something could be heavier than another one, and that's your specific gravity. I'm going to give you some examples of these and how this actually works in our use of materials. So, for example, these are some examples of sulfur. Sulfur is a native mineral, and it's just sulfur. We call it native because it only has one thing in its chemical composition, sulfur. And we use it a lot to ignite gunpowder and other things at lower temperatures. We put that sulfur in that gunpowder, and then you can actually light it at different temperatures. That's the same thing for a match. When you have like fireworks and things like that, you often have this kind of rotten egg kind of smell to it, and that is sulfur, and it actually helps to make the fire burn at lower temperatures. Now, we can get sulfur from its elemental form like this, okay, or we can get it in its crystalline form in pyrite or fool's gold, where it's an iron sulfur. When we separate those two, we can then get sulfur from it and iron. So we can mine pyrite to get both iron or sulfur from different materials. Okay, now the use of this one for lowering temperatures is a great use for sulfur, right? And the bonds of these, we have to break those bonds to be able to get those materials. In this case, yellow sulfur has a great yellow property to it. Okay, so does pyrite. It has this kind of goldish kind of yellow to it. But if I actually put pyrite and streaked it, it would actually give kind of a reddish hue to it. Well, it gives it a reddish hue to it because of the iron in it, and iron likes to oxidize, okay, or rust. And so you can get that to it. But also, another special property of pyrite is if you smelled it, you'd actually have that smell of sulfur to it because it has that sulfur within it. Okay, so these are different properties that can help us understand these materials. Now, hardness is determined by its bonds, right? So the crystalline nature of that bond and the different strength of those bonds. For example, in graphite, which is your pencil leads, all your pencil lead it's not pure graphite. It actually has graphite with some clays and other things in it to make the lead itself, the pencil lead, different hardnesses. Now, it's so soft that we write with it all the time. But if I actually pressurize that pure graphite, inorganic graphite, as much as I possibly can to force the bonds to bond in different ways, I could get a diamond, right? And diamond is made of the same chemical composition. Graphite's made of carbon, so is diamond made of carbon. But they do have two different chemical structures to them. So therefore, they're two different minerals. Same chemical composition, different chemical structure. Okay, so therefore different minerals. And so the bonds of this one have very strong covalent bonds, really strong bonds, whereas this one has strong bonds in one direction but weak bonds in the other direction. So therefore they leave behind when I write with my pencil, right? Okay. So here's another one for hardness. Garnet's a great example for hardness. It has a mole hardness of about 7 or 8. Most hardness is just the scale on which we put hardness on. Okay, and we often will put things like garnet in sandpaper because it's a great abrasive. Because it's so hard, we can use it to sand my wood or that I'm working on for my woodworking project or whatever. Or sometimes we put diamond in bits of drills to drill into the ground because it's actually harder, or on saws to make things harder, right? So or you can have talc, which is really soft. Now, talc is often used in baby powder because it is so soft to help moisturize your baby's bum, right? Okay, to make it so he doesn't get rashes. So the point comes is that hardness is characteristic by the bonding of the material itself. Now, color we use for lots of different things. For example, in the hematite here, hematite is iron, has lots of iron in it, and because it has all that iron in it, we can take that iron out of the mineral and use it for steel, making of steel and other things with which we use iron with, right? So steel is just one of those metals. Now, goethite or limonite here is yellow. So if we actually take that yellow out of that yellow material, put it in, and we can use it in dyes for yellow paint and things like that. For malachite, we can use it for its green color in paints and other dyes for green, right? Or azurite is another example of one which we can get for blues. So we can use it for dyes based off of the color that we have for those uses. Specific gravity is how dense something is. Galena has a high specific gravity because it has a lot of lead in it, and lead tends to be heavy. Okay, so we can extract that lead from the galena to get lead, or even we can do it for sulfur. Now, gold also has a high specific gravity. It has one of the highest specific gravities of almost any element. It has a gravity of almost 20, which means that for 1 pound of gold would equal basically 20 pounds of water, because basically what it is it's based off of the specific gravity of water, if I remember right. Okay, so if you had 5-gallon bucket of water weighs 40 pounds, how much would a 5-gallon bucket of gold weigh? Well, it would weigh about 600 pounds. It's a huge difference, okay, if you think about it. Okay, so luster, remember, that's how it shines. So often with things that have high lusters, we like to use for jewelry, okay, or we can use it for other things, like for reflection, like in a mirror. Or we can get for things for its cleavage. We could actually use it to break into sheets, to actually use for insulation, like we do in the micas. Okay, for solubility, calcite actually is soluble, and so it's something that we can get calcium into our bodies for. So, for example, calcite will react with acids. So when you eat Tums, which is just lots of calcite, when you put it into your body, it will react with your stomach acids, and therefore lower your pH in order to give you basically will help you to overcome a stomachache, right? Okay, so calcite is in a lot of different things. It's also in your teeth and bones and stuff like that. So our bodies need them all the time. So we extract that calcite from different minerals like limestone, and then put it into our bones. So we have calcite in our milks and our like Cheerios, toothpaste, stuff like that to strengthen our bones, right? Now, electrical conductivity is also a property. Now, sometimes when the electrons are flowing through a mineral, the electrons are shared with other elements, right? And if you put them together and the electrons shared all throughout it, then we have something that has a high electrical conductivity. So things like copper, gold, silver are also things that have high electrical conductivity. So we will mine gold or mine copper, or even chalcopyrite, which is a copper iron sulfate, so we can get iron, sulfur, or copper from. We can mine that to get all three of those materials for our copper wires. Okay. Another one could be the electrical conductivity, but instead of allowing electricity to go through it, not allowing electricity to go through it. So clay minerals could actually be used for not allowing electricity to go through it. So it doesn't allow electrons to transfer through the mineral, and therefore it actually can be used as an insulator. So ceramic insulators can be used in power lines to be able to make it so the actual, if you such a power pole, it's not going to electrocute you, right? Or it could even be used for your ceramic cups, because that's insulation for your coffee or hot chocolate or whatever hot drink, tea, whatever drink you're drinking. Okay. Another property that can be used is in quartz, so we can use in our watches. So if you ever heard of a quartz watch, the reason we use it is because quartz, if we put electrical currents in it, will shake or basically the atoms shake back and forth, and that shaking or that movement is what we're actually telling time by. Okay, and the movement of each of one of those crystals as we apply a lot of electricity to it will actually allow us to tell time. Okay, and so it's also used in other things for transformers and motors and things like that, because of how it actually shakes or moves as it goes through it. Right. Okay. Now, different mineral materials have different classifications. How would you all just classify these things based off of their different mineral groups, or how they react with one another and how they actually form together? Okay. There's 7 major mineral groups. The number 1 is silicates. Now, that shouldn't be a surprise to you, because remember, silicon and oxygen, which is what quartz is made up of, which is, by the way, the most common mineral in the world, is actually that's silicon and oxygen. And because those are the silicon and oxygen, the most common elements in the world, in our crust, then therefore they also should be the most common as well. Native elements would be things like sulfur, gold, silver, things that are just by itself. Halides are things that are from the halide group in the periodic table, okay, like halite or salt. Carbonates are like that have carbonates in them. Oxides, oxygen, iron, sulfates, sulfur, and sulfides.